Hello, my friends. Today we are going to talk about DC motors. Here is a cross-sectional view of a DC motors. Basically, right, it has uh, a stator. The stator will include the yoke uh, and the poles, and it also has a rotor. The rotor contains the armature and the armature windings. So basically, the motor, just like any other motor, it has two pieces. Yeah, the uh, stator. Stator is the device that doesn't move. Uh, the stator will have the yoke, which supports the poles, and the poles will uh, is either made with permanent magnets or electromagnets. Or electromagnet. And it also has a rotor. The rotor will contain the armature core and the armature winding. Armature winding. And this winding can be net wind or wave wind. Now, suppose the total number of poles is Z. Now, this is just the basic information. We don't need this. We will need this just for basic understanding. But the basic understanding of the motor is not going to be enough for the examination. So now, let's be realistic. Suppose uh, we are going to derive a equation for the back EMF. So the back EMF is the EMF for the armature. Then what we need to do is to take around this to make use of Faraday's law. By Faraday's law, uh, the EMF, the back EMF is going to be d flux dt. Yeah, it has a minus sign as well. Now, for the motor, we can find out d flux and dt. D flux is how much flux change, and dt is how much time that has been changed, that has been taken for the flux change. So now, what we can do is, right, we consider only one revolution. Consider only one revolution. uh, dt d flux is going to be equals to the number of pole, say the number of pole is p, and also where the magnetic flux per pole. And then this is just for one single conductor. Right? So now let's write down where P is the number of pole. Yeah, this is here the number of poles is 4. 1, 2, 3, 4. So this is number of poles. And each pole um, will generate some magnetic flux. So phi here is the polar flux. And now, what is delta T? Yeah, again, we consider only one revolution. How much time do we need for one revolution to take place? So what dt is going to be the speed of the motor, say n, right? Then the amount of time to be taken for one revolution is 60 divided by n. So where n is the motor speed. In RPM, revolution per minute. So if we substitute these parameters to equation 1, what we are going to get is substitute d flux and dt into 1. So what we are going to get, we will get the back EMF for one conductor equals to divided by 60 times n. So E is the back EMF for one conductor. Conductor means the copper in one copper in each of the in those copper slots here. And now there will be n the amount now the total EMF is going to be the number of conductors, the total number of conductors wind together. Yeah. So the EMF for the rotor, for the armature, say called EA is going to be minus and then V divided by A, and then P and 60. And what is Z? Z is the total number of conductors. Yeah, you have total number of conductors here, but some of the conductors get short together because of the parallel path. So you also need to say, right, A is the total number of parallel path. Now, if you have this piece of information, then it's pretty much enough. But you also need to say this, right? A is equal to P for lap winding. Because the armature can be lap wind or wave wind. So now A is equal to 2 for, for wave winding. So this is the basic information for the DC motor. If you have any question, please leave your question in the message, in the comments box. Thank you very much for your support.